So as we see the various topics that we have covered in the previous videos of the same chapter, there it was the input signal denoted by x of n in general notation here. So x of n was having the desired signal component that it was denoted by d of n along with the noise component, generally v of n here. And thereupon the picture it was like to have minimization of the mean square estimation of the desired signal, or you can say a discrete time random process denoted by d of n from the measurements of the related process x of n, as I have discussed here. So now in the current topic that it is titled adaptive recursive filters, we are going to have attention towards the problem of designing the IIR adaptive filters. So the earlier discussion was for the FIR. FIR stands for the finite impulse response. It is also known to be by the name non-recursive type of the filter, and of course in this particular chapter a type of adaptive filter here. Whereas IIR standing for the infinite impulse response, it is also known by the recursive type of the filter. So here the recursive adaptive filter here, or our current topic title adaptive recursive filters. See, mathematically the representation of the adaptive recursive filters can be given as y of n is equal to the summation k is equal to 1 to p or the multiplication of a suffix n of k to y of n minus k added by the summation k is equal to 0 to q or the multiplication of b suffix n of k to x of n minus k here. So in this notation, a suffix n of k and b suffix n of k are the coefficients of the adaptive filter at the time n here. Now, as with the case of the linear shift invariant filters, which we can also say to be the non-adaptive type here, the recursive adaptive filters here are potentially having an advantage over the non-recursive filters in providing the better performance for a given filter order. So filter order is nothing but the number of filter coefficients. Generally we are denoting it by small p or small q here. Now with the adaptive recursive filter, there are potential instability problems that may affect the convergence time as well as the general numerical sensitivity of the filter here. So let us have the example where we are having the consideration of the channel that is utilized for transmission of a signal denoted by d of n, that will introduce an echo, so that the received signal here we mathematically denote by x of n is equal to d of n added by alpha times d of n minus, it should be capital N here. Now here mod alpha should be less than 1 and the capital N is the delay associated with the echo. If both the alpha and capital N are known to us, so that time the ideal echo canceller for recovering d of n from x of n is an IIR filter that has a system function provided by the equation capital H of z. The representation is here into the z transform domain. So this is equal to 1 upon 1 minus alpha times z to the power minus capital N here. However, since we have alpha and capital N to be generally unknown in the practical cases and possibly time varying also, so that time it is more appropriate for the echo canceller to be an adaptive recursive filter here. So this is our topic of interest. And although we could have consideration of a non-recursive adaptive filter instead of the current, the order of the filter required for sufficiently accurate estimate of the desired signal d of n may be very large here. So for example, suppose that the inverse filter denoted by h of z is expanded in the geometric series, the mathematical representation which we can provide as capital H of z is equal to 1 upon 1 minus alpha times z to the power minus n from the previous equation. This is equal to the summation k is equal to 0 to infinity for multiplication of alpha to the power k with z to the power minus n into k here. So if small p is large enough so that the mod alpha to the power p is very less than 1, then we could form a finite order approximation to the filter function denoted by capital H of z. So this one can be denoted as capital H cap of z, that is equal to the summation or the index variable k is equal to 0 to p or alpha to the power k multiplied by z to the power minus capital N into k here. So we have the consideration of the adaptive non-recursive eco-canceller here. The form can be denoted by d cap of n, that is equal to the summation k is equal to 0 to capital N multiplied by p or the multiplication of b suffix n of k to x of n minus k here. However, if alpha is very near to 1, which forces small p to be large, or if capital N is very large than that of the 1, then the order of the adaptive filter, here we have denoted by capital N multiplied by p, required to produce a sufficiently accurate approximation to the inverse filter may be very large for this to be a viable solution here. So let us start for the adaptive recursive filters with a derivation of the conditions. Those are necessary in order for the coefficients of the recursive filter to minimize the mean square error. The mean square error can be denoted by the Greek symbol xi or zeta here, xi of n. This is equal to the expected value of mod square of E of n, where this E of n, the signal we have already known from the block schematic of the adaptive filter here. This is the difference signal. So d of n minus y of n, the difference between desired signal and the output of the adaptive filter. So y of n is the output of the adaptive filter, whereas d of n is the desired signal to reach the destination here. So let us have the initial assumption that the filter is first of all shift invariant. So first of all we shall be focusing on the non-adaptive case here, and then we shall be going for the adaptive case for the practical use here. So here we have y of n, that is equal to the summation L is equal to 1 to p or a of L multiplied by y of n minus L. This term is added to another term where again we have summation. This time L is equal to 0 to q for b of L multiplied to x of n minus L here. Now in this case, if we have capital theta to represent a vector of filter coefficients a and b together, here we show theta, capital theta is equal to the column matrix here, where we have the first element denoted by the vector of small a and the second row element is vector of filter coefficients b here. These two are vectors basically, and when we have the representation with all the elements belonging to the vectors a and b, so here we can denote the capital theta to be the transpose of, we have a of 1, comma a of 2, comma a of 3 up to a of p. Afterwards we start with b of 0, comma b of 1, comma b of 2 and so on up to b of q here. Let we have the notation small z of n, that is representing the aggregate data vector. Mathematically here we denote z of n, that is equal to a column matrix where the first row element is y of n minus 1, whereas the second element is x of n here. This we can also express to the form transpose matrix. Here we have the first element y of n minus 1, comma y of n minus 2, comma y of n minus 3, and so on up to y of n minus p here. Next to that we continue with the values of x of n and so on up to x of n minus q in the transpose form here. Now for this non-adaptive case, let us have the output of the filter at the time n expressed in terms of this capital theta having the vector of the filter coefficients along with the z of n that has denoted the aggregate data vector here. So we have the output y of n that is equal to small a transpose multiplied to y of n minus 1. The term is added by small b transpose multiplied by x of n. So combining a and b, the filter coefficients, into the transpose form, here it will be the capital theta transpose multiplied by the aggregate data vector z of n here. Now in order for the capital theta to have minimization of the mean square error denoted by xi of n, that is expected value of the mod square of small e of n. So we can replace it as expected value of mod square of the difference, where we have subtraction of y of n from d of n. So here it is very necessary that the derivatives of this mean square error with respect to each of the coefficients, here we take the complex conjugate of a of k and complex conjugate of b of k be equal to 0. So therefore the gradient vector will also be resulting into the value 0. So as we have the gradient notation for this mean square error, here we have del xi of n is equal to del expected value of mod square of e of n. So we write it as expected value of del is applicable to the mod square of e of n, and finally we represent it as expected value of e of n multiplied to del of complex conjugate of e of n. So therefore the gradient will be equated to the value 0 when we have the condition satisfied. The expected value of e of n multiplied by grad of the complex conjugate of e of n is equal to 0. This is very important condition. Now as we know that e of n is a difference signal here, the desired signal minus the output signal, so e of n minus y of n. So that time grad of complex conjugate of e of n is equal to minus grad of complex conjugate of y of n. So therefore the previous representation of the condition will get a modified form. Here we will have it as the expected value of e of n multiplied by grad of the complex conjugate of y of n, and this value equated to 0. So here looking back to the condition here, we define the next step or evaluation of the gradient of the complex conjugate of y of n. So it will be possible by having differentiation with respect to the complex conjugate of a of k and b of k here. Now in forming these two types of the derivatives, it must be kept into the consideration that the output signal y of n depends on y of n minus l for the L values to be 1, 2 and so on up to small p, and each of these in turn will depend on the filter coefficients A of k and B of k. So therefore the partial derivatives of the complex conjugate of the output signal y of n with respect to the complex conjugates of A of k and B of k are given by the two equations here. So first of all we have del complex conjugate of A of k for complex conjugate of y of n. So this will be equal to the complex conjugate of y of n minus k added to the summation L is equal to 1 to p for the multiplication of complex conjugate of A of L to the partial differential of complex conjugate of y of n minus l with respect to the complex conjugate of a of k here, where k is equal to 1, 2, 3 and so on up to small p. Whereas the next equation is having the left hand side represented by the partial differential with respect to the complex conjugate b of k for the derivative computed for complex conjugate of y of n, that is equal to, in the RHS we have the first term complex conjugate of x of n minus k added by the summation l is equal to 1 to p for complex conjugate of a of l multiplied by the partial differential of complex conjugate of y of n minus l with respect to the complex conjugate of b of k. Here k starts at 0, it extends 1, 2, 3 and so on up to small q here. So these are the two partial differential equations here. Now getting these two equations into the vector form, we have the new representation for the gradient vector, we can say. So here we write grad complex conjugate of the output signal y of n, this is equal to the complex conjugate of z of n added by the summation l is equal to 1 to p for the multiplication of complex conjugate of a of l with the grad of complex conjugate of y of n minus l here. So here we have z of n, that is the aggregate data vector, already we have defined in the previous equation here. So the combination of the two previous equations, we have the two conditions, those are really very necessary for the filter coefficients a of k and b of k to minimize the mean square error. So on this slide we have the equation number 2 and equation number 3 defining these two particular conditions. So the first one is expected value of the bracket inside which we have the error signal e of n multiplied to the complex conjugate of the square bracket that has y of n minus k added by the summation l is equal to 1 to p for a of l multiplied to the partial differential of y of n minus l with respect to a of k. So this is all equated to 0 provided k is equal to 1, 2, 3 and so on up to small p. Whereas the second condition is that the expected value of the bracket is equated to 0, where inside the bracket we have e of n multiplied to the complex conjugate of the square bracket that has the first term x of n minus k added to the summation l is equal to 1 to p for a of l multiplied to the partial differential of y of n minus l with respect to b of k. So here k is equal to 0, 1, 2, 3 and so on up to small q. Now after looking at these two equations, we observe the non-linearity here. So because of the non-linearity here, it is quite difficulty for finding solution at the optimum filter coefficient levels here. So therefore these two equations are not generally directly solved, whereas the approach of the steepest descent methodology can be opted for searching out the solution in iterative fashion, which will be more local rather than a global minimum here. So here with capital theta suffix n, the estimate of the solution at time small n can be represented. Here we have capital theta suffix n is equal to the column matrix where we have the first element vector a suffix n, the second element vector b suffix n, which is actually in the transpose form a row vector. We have an of 1, an of 2, an of 3, this way up to an of p, followed by bn of 0, bn of 1, bn of 2 up to bn of q here. So now as we are going to make the use of steepest descent methodology approach here, The update equation for the capital theta suffix n can be provided in mathematical representation. We have theta suffix n plus 1, that is equal to theta suffix n minus the step size representation mu multiplied to the grad of the minimum mean square error, that it is psi of n here. So mu step size and the gradient vector we have on the right hand side second term here. Now in this representation there is one difficulty, that the gradient vector will involve the expectation term here. See, the gradient of psi of n is equal to minus the expected value of e of n multiplied to the gradient of the complex conjugate of y of n. So it is very clear that unless the required ensemble averages are known to us, the steepest descent algorithm cannot be directly implemented here. Now, if we can't have the steepest descent algorithm directly implemented here, we have a choice to utilize the LMS adaptive filtering approach here. Both the approaches we have studied in the previous videos of the same chapter here. So thereupon it will be a replacement of the expected values by the instantaneous values here, and instead of the direct gradient of psi of n, here we will be having the estimate. So del cap of psi of n, that is equal to minus e of n multiplied to the gradient of the complex conjugate of y of n here. So therefore the update equation that we have considered previously will get a modified form according to the LMS adaptive filtering structure here. So this will be capital theta suffix n plus 1, that is equal to capital theta suffix n added by mu multiplied to e of n into the grad of complex conjugate of y of n here. Now the expression in terms of the filter coefficients respectively an of k and bn of k also we can provide. So for the filter coefficients an of k, we have the equation a suffix n plus 1 of k is equal to an of k added by mu multiplied to e of n into the partial differentiation of complex conjugate of y of n with respect to the complex conjugate of a suffix n of k. Whereas for the another type of the filter coefficient denoted by small b suffix n of k, we have the equation b suffix n plus 1 of k is equal to b suffix n of k added by mu into e of n into the partial differentiation of the complex conjugate of y of n with respect to the complex conjugate of b suffix n of k. So here the partial derivatives can be evaluated with respect to the earlier representation with the filter coefficients a of k and b of k replaced by the time varying coefficients a suffix n of k and b suffix n of k. So the new equation for these two filter coefficients we have in the previous fashion, the new form, it is del complex conjugate of a suffix n of k for complex conjugate of y of n, that is equal to the complex conjugate of y of n minus k added by the summation L is equal to 1 to p for the multiplication of complex conjugate of a suffix n of L to the partial differentiation of complex conjugate of y of n minus L with respect to the complex conjugate of the filter coefficients a suffix n of k. K will be holding the values 1, 2, 3 and so on up to small p. Whereas the second equation will be having the left hand side denoted again having the partial differentiation of the complex conjugate of y of n with respect to this time the complex conjugate of the filter coefficient b suffix n of k. So this will be equal to, on the right hand side we have the first term complex conjugate of x of n minus k added by the summation L is equal to 1 to p or the multiplication of complex conjugate of a suffix n of L to the partial differentiation of complex conjugate of y of n minus L with respect to the complex conjugate of b suffix n of k. So here k will start at 0, 1, 2 and so on up to small q here. Now these two equations along with the earlier representations on the previous slide, the filter output equation we give directly as y of n, that is equal to the vector notation a suffix n transpose multiplied to y of n minus 1, further added to the transpose of the vector notation for filter coefficients b suffix n multiplied to x of n, which is equal to the transpose of capital theta suffix n, the combined representation of the two types of the filter coefficients, multiplied by z of n, where z of n is the usual notation that we have described earlier. So this is the very important equation. This equation you can make outline here. This important equation you can call to be the infinite impulse response LMS algorithm here. So as our current topic is adaptive recursive filter, as I have already made it clear that whatever we have learned so far in this particular chapter, that was concerned to the design of the finite impulse response filters, what we can treat to be the non-recursive type filters here. Here we are making the use of the popular LMS algorithm for the adaptive filter design, but this is for the IIR case, that is the recursive filter. So up to this equation the derivation should be made if the question is like this. So this is the important equation for the current topic, adaptive recursive filters. Now as we can compare this particular representation with the FIR, that is finite impulse response LMS algorithm here, which we have covered into the sixth topic for the convergence of the LMS algorithm here, we will find that the IIR LMS algorithm is having very slow convergence with respect to the filter coefficients that minimize the mean square error here. So therefore, first of all, we shall have a focus on the derivatives of the complex conjugate of y of n minus L. We have represented in the earlier two top equations on this particular slide, which has been utilized to give the resultant equation here. So for making simplicity for better convergence here, we can have the notation for the partial differentiations, that the partial differential of the complex conjugate of n minus L with respect to the filter coefficients a suffix n of k in complex conjugate. So we can replace it to the partial differentiation of complex conjugate of y of n minus L concerning the complex conjugate of a suffix n minus L of k. And also similarly for the second equation, we can have the replacement of the partial differentiation of complex conjugate of y of n minus L by the differential of the complex conjugate of b suffix n of k replaced by the partial differentiation of the complex conjugate of y of n minus L with respect to the complex conjugate of b suffix n minus L of k. So here the approximations to the two differential equations we can give like this. We have again the two equations. The first equation, it will be the partial differentiation of the complex conjugate of y of n concerning complex conjugate of the filter coefficients a suffix n of k into the vector form. Very similar to the RHS, here it will be complex conjugate of y of n minus k added by the summation L is equal to 1 to p for multiplication of complex conjugate of a suffix n of L to the partial differentiation of complex conjugate of y of n minus L concerning a suffix n minus L of k complex conjugate. Whereas the second equation, we have the approximation of partial differentiation of complex conjugate of y of n concerning complex conjugate of the filter coefficient representation in vector form b suffix n of k, very similar to or approximated to complex conjugate of x of n minus k added by the summation L is equal to 1 to p for the multiplication of complex conjugate of a suffix n of L to the partial differentiation of complex conjugate of y of n minus L with respect to the complex conjugate of b suffix n minus L of k. So now in the new representations, as we have involvement of the delayed versions of the derivatives, we can say that we have shifted from the non-recursiveness to the recursiveness. Hence our topic is the adaptive recursive filters. So here let us denote the approximations to the partial derivatives. Those have been generated by the recursion process by psi suffix k of n to the power a and psi suffix k of n to the power b. The corresponding two equations here we denote. First of all, the approximation is with respect to the complex conjugate of y of n minus k added by the summation L is equal to 1 to p or multiplication of complex conjugate of a suffix n of L multiplied to psi suffix k of n minus L. Psi is having the power small a, whereas the second equation is for psi suffix k of n to the power b for the psi that is equal to the complex conjugate of x of n minus k added by the summation L is equal to 1 to p for the complex conjugate of a suffix n of L multiplied to psi suffix k of n minus L. Psi is having the power b here. Now let us have the illustration to be discussed here for the approximations generated by filtering the complex conjugate of x of n minus k and the complex conjugate of y of n minus k with the shift varying recursive filter having the function 1 upon capital A suffix n complex conjugate as a function of z asterisk here to denote the complex conjugate here. So this illustration is just simplifying the understanding what this particular filter function is going to make here. The approximations that you can see on the right hand side for the concerned inputs to be the complex conjugate of y of n minus k and the complex conjugate of x of n minus k here. Now let us have a look onto a block diagram of this simplified infinite impulse response LMS adaptive filter. So here it is the block schematic. So from this block schematic it can be noted that p plus q plus 1 times recursive filters operating into the parallel fashion are producing the approximations as we have described in the earlier equations to the gradient vector here, and the outputs of these particular filters are utilized for the updation of the coefficients of the adaptive filter here. Now the algorithm concerning the infinite impulse response LMS filter structure we have in a tabulated form summarized in these steps here. So it will require the parameters p comma q to be the filter order correspondingly. Mu will represent the step size. We have the initialization of a suffix 0 and b suffix 0 from the value 0 here, and we have to make the computation for n is equal to 0, 1, 2 and so on. For we have y of n described as transpose of the filter weight, that is a suffix n multiplied to y of n minus 1, further added by the transpose of b suffix n multiplied to x of n here. Whereas we need to also make computation of the error signal e of n to be d of n minus y of n, and for k is equal to 1, 2, 3 and so on up to small p, we have to make computation of the approximate psi suffix k of n to the power a, where the update equation for the concerned filter coefficients is a suffix n plus 1 of k is equal to a suffix n of k added by mu multiplied to e of n into psi suffix k of n power a here. And at last, for the values of k starting at 0, 1, 2, 3 and so on up to small q, we have to determine the approximation denoted by psi suffix k of n to the power b, and the update equation for the filter coefficient is denoted by b suffix n plus 1 of k, that is equal to b suffix n of k added by mu times the error signal e of n and the approximation psi suffix k of n. Psi is having the power small b here. These all equations we have just now covered, and summary of it we have given in this particular tabulation. So this was the discussion with respect to the simplification with the help of the two types of the approximations that we have made and represented by psi suffix k of n to the power small a and small b. And practically there shall be again the computational load here, and the scope of making more simplification we find in another approach where we can have the assumption that the step size that we have been denoting by mu is very small here. So let us have again the illustrations concerning this particular approach to have simplification of the computational load here. So in this simple approach we have the first illustration where we have the gradient approximation formed by filtering the complex conjugate of y of n minus k with the shift varying recursive filter 1 upon capital AN complex conjugate as a function of the z asterisk here. Whereas the second block schematic you see, or the assumption that the filter coefficients are slowly varying, the delay and the recursive filter here we can interchange here. And lastly we see the resulting simplification to the infinite impulse response LMS adaptive filter with the help of this block schematic here. Now for this particular case, the equations for the filtered signal approach to the adaptive recursive filter we summarize with the help of this particular tabulation, where as the similar case we have discussed just now, parameters are the same p, q and mu. Initialization here we have same for a suffix 0 and b suffix 0 to start at the value 0, and we have to make the computations represented by the equations into the part a, b, c and d. So this was our topic, adaptive recursive filters.